Okay, welcome back. This is the second half of Chapter 4. So it's 4b or not 4b? Is it nobler in the mind? Okay, so we left off on page 94, getting ready to introduce the radix sort. Now the radix sort is really strange. It doesn't actually compare the values in the array. You think, well, how the heck does it sort then? What it uses is it takes the data and puts it into buckets, so to speak, so that here's your original list of numbers. What it does, it creates a series of buckets. Okay, looking at this list, you can tell it creates a set of buckets. So a bucket is basically just another array. And so the first bucket is everything that ends in a 0. And then bucket number 1 is everything that ends in a 1. And bucket number 2 is everything that ends in a 2, etc., etc., etc. So what happens is, like if you had a 4-digit number, it's going to create 4 buckets. It's going to have a bucket for this, and then a bucket for the second decimal place, and the third decimal place, and the fourth decimal place. And then once you've got those guys sorted the way you want them, then you just pick them. I'll take that one, and that one, and it makes the sort complete. So it's actually pretty doggone efficient. They talk about an example in the book, which is kind of hard to visualize, but can you imagine, you know how people have like tab dividers, like index cards or something? Well, if you had a tab on a card, you have a physical card, it has a little tab in it, and the tab has a hole in it. And then over here you have another tab with a hole in it, and over here you have another tab with a hole in it. Well, back in the day, apparently, if you wanted to pull out all the ones that had, whatever the first hole is, you stick a metal rod through that hole in the thing and kind of shake, and all of those cards would come up. Okay, it's kind of a funky example, but it's not difficult to figure out once you look at it this way. So in our case, what we're probably going to do is we're probably going to separate by ones, tens, hundreds, thousands, right? Okay. So this example on page 96 is supposed to show how it works. In this case, the first pass is on the ones digit. That's kind of hard to describe. Now, this actually becomes pretty doggone efficient, but can you tell that I'm going to need one heck of a lot of buckets? So let's say you had 100 numbers, okay? And each number was 10 digits long, okay? Then I need 100 times 10 amount of storage to pull this off. So that's a lot of memory. In other words, I take the original array, okay, and if there's 10 digits in there, I need 10 times the amount of size of the original array. Whew. Now, in some scenarios, that is not an issue at all. No big deal. But for general purpose computing, no. A lot of people don't use the radix sort, even though it is remarkably efficient. Okay. So space efficiency, space complexity becomes an issue here, big time. And so each element is compared m times, m being the number of digits, okay? So in this case, it looks like there's only a 3-digit number being looked at, okay? So each number we looked at m times. So if I was to look at this from a big O notation, the big O notation would be n times m, n being the number of elements in the array, and the m being the width. So you kind of look at this as length and width, right? If you were looking at this from a two-dimensional matrix point of view, that's the length times the width. Okay, cool. All right. So in big O notation, multiplying times a number like 3 or 5 really isn't all that relevant. So we actually, remember the point of the big O is not to predict the exact execution time. It's to give you a feel for how it's going to behave. So they actually simplify that by just doing this, even though it's not, technically that's correct, because we're after the shape of the curve. Remember, The big O is going to tell me the shape of the curve. So the shape of the curve is linear. That's the point here. And up to now, that is the absolute best performance we could possibly have out of a sort, is to have linear. Because the ones prior to that were like, in squared. Like, ooh, right? So this is good. So, is there a catch? Yeah, I already told you what the catch is. The catch is that, this is a heck of a lot better than n squared by a huge margin. But the space complexity just makes this not really viable for an awful lot of things. It takes an awful lot of energy to set it up and stack in most applications. When you create an array, it actually creates it on a chunk of memory called the heap, and the heap is the part of memory that gets manipulated from time to time with garbage collection, and so it's not perfect. Okay, so one more time. So let's say to talk about how unattractive this thing is. Let's say you have a database field, for first name. Okay, and it's 50 characters long. That sounds about right, So if I wanted to sort that, and let's say I have 1,000 rows. 1,000 rows in my database. And I have a field with 50 characters. So that would be 50 times 1,000. Yeah, that's 50,000 size of my array. Most people don't do that. So, number of digits, most likely you're not going to have, 50 digits in your number. I guess you could. Now, I have seen versions of the radix sort that use what's called a binary sort, which they if you give it an integer, they assume that an integer is going to fit in 32 bits. Instead of using tens, 1, 10, 100,000, 10,000, they use the binary version of that. So they have 32 buckets. They don't have to stop and ask, what's the size of the integer, because we can just do it ourselves by just assuming that everything will fit in 32 buckets. Okay. So how bad is the idea of creating an array of 50,000? Well, in C# and in Java, it's not terrible. Okay, it's not terrible, but it also isn't good. The amount of memory this thing has to consume and then release is a lot. So let's look at the algorithm. And so their algorithm in the book is obviously missing. They have this thing called append and combine, which they don't actually show anything. That's not exactly how we're going to do it. The way we're going to do it is looking at the hints file. So here's how we're going to do it in our stuff. Now, the way they start this thing up is they want to know what is the largest number of items in the list. And the idea is, if there's only 4 digits, well then I only have to create 4 buckets, right? But I need to know what is the biggest number on the list. If the biggest number has 6 digits in it, well then, I have to have 6 buckets. So this little routine for getting max is a little annoying, because I have to pass through the array one time before I find out what the biggest number is to figure out how many buckets that I need to have. Okay, and that's a little weird. So this routine is using the modulus operator. All of the languages have a modulus operator. So yes, this is actually easier to do than the technique shown in the book. Like if I was to do, log 10 of the list, and then, do a math floor on it and, all the rest of that stuff. So I don't have to do any fancy mathematics. I just need to scan this guy. Okay, now, you might think, well, this is not very efficient if I have to scan through it one time. Well, there is another technique that starts, instead of starting, remember now, the very first run through the list, okay, the very first run through the list, you could start at the big end, right? Like let's say we have 3 digits, so you could start at the hundreds and then the tens and the ones, right? But if I start at the ones first, well then I can use that to when I go through and build my ones, I can also figure out which one of those is the biggest one. And then, so if I'm moving from left to right, it's a lot easier than right to left. Although that's not what this algorithm is doing. And we are going to use this algorithm. Okay, so there is some discussion about, once again, if you had a linked list or an array list, or it goes by lots of different names, instead of moving things like into separate arrays, I could just move them around. I could just scoot over and insert something in the middle. I could reduce the space complexity issue down to practically nothing. But I have to have it in an array list, and I don't have an array list, so that's not something that we're going to do, but you need to know a little bit about it. You need to know that, you know, the idea of a radix sort is actually pretty cool, but its implementation is what's kind of holding it back. Okay, so how do you find the number of buckets I need? What it's called, the key size. How do I find the key size? Well, it would be like the log 10, not log 2, but log 10 of whatever the biggest number is. So if your biggest number was 9999, then the log of log 10 of that is 4. Okay? Got it? Good. Okay. I mean, you don't even need to use a log function if you just count how many digits that is, right? 9999, there's 4 digits, kind of sort of done, right? Okay, good. All right. So, remember this thing is kind of sort of like a 2-dimensional matrix, and so it's actually, its performance is pretty good up to a point. Okay, and so it's most optimal when the log of n is greater than the number of digits, okay? That makes sense? Log of n is greater than the number of digits. So, let's say I had 100 digits. I'm sorry, I had 100 digits, an array size of 100, but the k size, okay, was 8, okay? K size of 8. In other words, it's very wide. I already know the depth. Depth is 100. Log of 100 is 6 point something, right? So if the k size was 8, I begin to lose some efficiency. Does that make sense? So do you understand how the height and the width of this thing is what determines the efficiency? Okay, good. Okay, so an n, a big O of n? Woohoo! You're not going to get any better than that. It's just, this guy is just riddled with all sorts of things that just hamper its implementation. Fantastic idea, poor implementation. Okay, so let's move on. So in a heap sort on page 98. Okay, this thing is based upon a binary tree, but not the exact same binary tree that we did the last time. You know, the last time when we did the binary tree, we did a binary search tree. So if I had a bunch of random numbers between 1 and 100, or not between, exactly 1 and 100, well then 50 would be at the top, right? And then it would split on either side. That's the way that thing works, if you recall. Well, that is not at all how this thing works. This thing is a heap sort, which puts the biggest element at the top, and then the other ones go underneath it. So it's not at all identical. Okay, we're coming up on the 15-minute mark. You guys know how this works.